Hello, welcome to ECE-222 Lab2 introduction. We're going to have a short introduction on how to approach the lab, what are the main goals, and then I will walk you through the process on Proteus to show you the template. So let's get started with this. So the lab goals are quite simple. You have to implement the LED halograph. You have the lab manual as the main reference document for this. The main goal for you is to become proficient in implementing subroutines and using lookup tables, aka arrays. Then we're going to go through the walkthrough, the code template. I recommend this sequence when you're implementing the subroutines: delete control, delay end, chart to Morse, and transmit Morse. I'm going to explain this in detail when I present to you the code, but I want you to have this as reference because I'm going to upload this presentation. So when you approach the lab, you know what is my recommended sequence of subroutines for you to implement. So let's get on with Proteus and the project. So I've already set up the project on Proteus. The first thing you will notice when you open the project for Proteus is this big black box here. Other than that, the design is the same. You have the same hardware, and I've added this logic analyzer that will help you debug your code. So there's a video for this already posted on Learn. I recommend you watch the video once you have the last routine, transmit Morse, in the process of implementation, when you are going to be able to see some sequences coming out of PA5 through the LED. Trying to debug this by looking at the LED is not going to be very helpful. So this is going to be your best friend for that purpose. Now, moving forward, let me show you the code. So for the project on Microvision, there's not much to say. You will create the project the same way, edit your code on the lab template. So you can see here the lab template is the same for the first part, but then we have this source code that contains the main loop and the prototypes for the subroutines, and finally the two local tables or arrays that we're going to be working with. But I feel that it's much better if I run this presentation through Proteus and on Microvision. So let's start running the code. So I already set up a breakpoint on the first line of code that really interests us. So we have a line of code here. So I'm gonna run up to that point. Remember, you can press F12 or run. I prefer to use the keyboard, it's faster that way. And so we're at this first instruction. So what is this instruction doing is it is loading the input LUT address onto R5. So this syntax may seem confusing to some of you, but it's not that difficult. So if I right click and disassemble, you are going to be able to see the actual instruction that is implemented here. So it's just LDR to R5 with the PC as the base address and 33 as the offset. So what's going on is that I have input LUT in memory, is this first table or lookup table at the end of the project, and this is not code, but this is stored in memory. And so what we have here is a DCB, so this is a table of characters, and if you look at it, it's just the sequence, the string bird with a null termination. So this is the equivalent that we have to a C string, and what you're going to do is to modify this string for whatever sequence you want to transmit using the Morse transmitter. I recommend you use SOS as debugging sequence because pretty much everybody knows that one, and it's going to have a very nice clearly defined pattern that you will be able to see in the logic analyzer. So this sequence, like I mentioned, is just a string, and then we have this Morse LUT, which is a completely different table. This one is declared as half words, okay? And so what we have here is the equivalent in Morse code for each of the alphabet characters in the alphabet. So for example, 17 will be A, 1D5 will be B, and so on. So there are two different ways you're going to be accessing these two. The first instruction we're looking at up here is the way we're going to be accessing the input LUT. For the Morse LUT, you're going to have to figure out yourself a way to approach that. But I'm going to give you some hints, and there are more hints in the code. So, like I mentioned, the first thing is to load that address onto R5, and then we're going to read the first character. So my expectation here is that I'm going to be able to read the B character. That is going to be 42 in hex, if I recall well. So let's do that. Okay, so we have 42. 42 is the equivalent in hex to the ASCII character B. And this order instruction here, what it's doing is checking whether we found the end of the string. Remember, the end of the string is the null character, which is 0. And if we find that, then we're going to branch to some more part in the code. Otherwise, we're going to keep continuing. And so this is the main program. We're giving you this skeleton or implementation of the main program. I just want to point out the important parts to follow up here. So let's keep moving. So this branch is not going to branch clearly because R0 is not 0. And so we now go into executing the branch instruction, which will not branch. And we reach this BL instruction. So what is BL? BL is branch with link. And the way this instruction works is that you need the instruction that follows this branch with link, so that we can return back from the subroutine. So now I'm going to use a different command in the debug menu to enter my subroutine. So I can just click here to get into, or press F11. So let's go with the mouse this time. And as you can see, what happens is that this branch with link instruction is an unconditional branch, and it will bring me to the chart to Morse subroutine. But while doing so, it will store, okay, the link address in the link register. And so what happens now is that you find this stmft. This is a new instruction to you. It's just a store instruction with some modifiers here, and these modifiers are telling ST how to handle the stack. So for details on this, you will have to go check the reference. But basically what's going on at this point is that I'm using R13 as the register for the stack. So this is pointing to the stack, to the bottom of the stack in this case, because the stack is growing down. That's what the D, for example, says here, that's decrementing. And I'm storing R14, which is just the program counter. Remember, as part of the execution of an instruction, sorry, I'm storing the link register. So remember, as a part of the execution of an instruction, we always compute the next address that we're going to execute. In the case of branch instructions, you have two different addresses. You have the next instruction in case the branch does not occur, and you have a target address in case the branch does occur. And with branch with link, you are going to branch anyways, but we're storing that next instruction address in R14. And what I'm doing here is I'm storing that in the stack. And so what you have to do when you reach one of these in subroutines is you have to push into the stack every register you modify, except those that are going to be used as output registers. So more details in the manual. Now what's happening here is that I reached the subroutine. The subroutine on its own has these big comments. You should read carefully all those comments because they have information that is very important. For example, for the input, you have to put the input in R0, so the character has to be here. In this case, that's exactly what happened. is already there, so you don't have to do much about that. But you have to keep in mind that all subroutines are going to have may have different input registers and so on. So the output is up to you to choose. You can return anything in any register that you prefer. Remember, registers that are used as return values will not go into the stack, and there are some warnings and some hints you should be aware of. So read everything here. Is not just empty text. It's going to help you succeed in your implementation of the subroutines. Now, these knobs for each subroutine are just there as to give you padding, so you know you're gonna override this knob with your own code and you're gonna build up your subroutine. So once we finish, in this case nothing is gonna happen, this subroutine, we're ready to return. And so the LDMFD, what it does, it takes everything that you've put into the stack and returns everything to the registers. And the difference in this case is that when we enter with STMFD, we store the link register in R14, and we store R14 onto the stack. When we go away from the subroutine, we are popping that value into R15, and R15 is the program counter. So by doing so, at the end of this process, we are going to be able to jump back to the next instruction after BL. There's another way we can do this. We can use the BX instruction for the return part, but in this lab we can just use LDMFD, which is much more convenient. You would use BX when you have to change mode. For example, now we are in the privilege mode for the CPU. If we want to change mode from privilege to user or something like that, we're gonna have to use BX anyways, or when we want to change mode from thumb to ARM and so on. But for this course, we can get away with this one. Okay, so and we want to make things simple for you. So let's go back. If I press F10 and execute the LDMFD, I go back, and now we are on the next subroutine, which is transmit Morse. So if when I enter that one, F11 will take me there. And so transmit Morse, this subroutine, it will take in the Morse code pattern you retrieved with a chart to Morse. And so we're going to process this Morse code that we're receiving in R0, okay, and we are going to send that out to the LED. And for that purpose, we need to use delay N and let control. So these are two new subroutines. Delay N, you can reuse the code that you wrote for lab 1, but now you're going to have to implement this as a nested loop. So you're going to have an inner loop that is going to be a fixed amount of time, and then delay N will take in a value in R0, okay, which is the delay value you want to have, and you are going to you're going to produce that delay, constant delay, that many times. So let's get this running. So let's enter delay N, and so as you can see here, delay N must use R0 as the input value, and R0 has to be greater than 0. So there's no way you're not going to modify R0 as part of the implementation of the previous subroutine. So like I mentioned before, we have these knobs. So you have the STMFD, the LDMFD. So whatever registers you don't use as output, you have to put in here. So this subroutine that you see, it has no output, and what you specify in R0 is the number of times you want to run that inner loop you're going to be putting inside this subroutine. So let's go back. If you want to finish the execution of a subroutine, you can just click here, is Control F9. Let's do this with the mouse. So we're back to transmit Morse. You have the branch with link to let control. So let control, let's get inside that one. What we'll do is, okay, again, we're using R0. This is on purpose. We're using R0, as the register in which we're going to provide the input values for LED control. Now LED control is going to be much different to what you may have implemented for Lab 1, because in this case the value specified in R0 is going to tell this subroutine whether you want the LED to turn on or turn off. It's not just toggling, so toggling is not going to work anymore. So you have to have full control of what you want. So let's get out of this one too. So they are here as an example, as a reminder that you have to use a delay N and control inside transmit Morse. So let's finish transmit Morse. So let's get away from this one. And now we're back to the main program. Okay, so you saw that as part of the section of transmit Morse, we had nested subroutine calls. Now we're back to the main program, and what we have here is an increment to the pointer, okay, for the input LUT. So this may seem not the way I usually recommend people to use the LDR. So let's go back. So as you can see here, we have LDR, a byte, right? Into R0 we want to have R5, and what I did is, instead of using for the LDR the base plus offset, I just incremented this pointer. If we go back to the input LUT, what we have is this string we are traversing sequentially. So it doesn't make much sense to have a base address and an offset when we can just increment the pointer by the right factor, and that will allow us just to read this this bird. Okay, and so we're incremented by 1 because this is just one character, and that's what we want to read. When you go to work with a Morse LUT, that method won't work, and the reason why is because you can have pretty much any combination of characters in the input LUT, and you need to fetch what is the Morse code value for that character, and in that case you're going to have to access this using Morse LUT as the base address. You can use something very similar to what you see for when we store in a register the address for input LUT in R5. So you can follow a pretty similar method, but then you're going to have to use the character that you get to compute the offset, and so that's up to you. You're going to have to figure out how you're going to approach that way, and then instead of using just LDR with one input parameter, you're going to have to provide 2. You're going to have to provide the base address, and in another register you're going to have to provide the offset. So let's go back to the main program where we're executing. So we're executing this LDR, and so what's going on here is that I'm fetching the next character. In that case it's going to be I, so we fetch that, and then we branch back to the test case. So we're not done with the instruction. We can keep processing them and sending the characters one by one to the LED, and once we finish with the string, which will happen now, as you can see R0 now turned 0, which means I read the null character at the end of the string, right? Now the TEQ instruction will change the flags in a way that the BEQ is going to branch, and when it branches to the end of the character. And so what I'm doing here is I'm creating that space that you have in the manual between strings, and so we put that space, we turn off the LEDs for 4 times, and then we're back to the main loop, and we start processing the string again, and the prompt just continues the execution. So I just wanted to show you this main program, because that is something we give as part of the template, and we also provide these prototypes for the different subroutines. So what you should do is read carefully all these comments, because they are part of the documentation that you have for this project. going back to the implementation of the subroutines, I would recommend that you go first with the let control, because it's very simple. It's just to pass two different values to that subroutine, and you can test that by calling LED CTL with different values. It just requires you to move using move instruction the value you want for 0 and the value you want for the LED on and the value you want for the LED off into R0, and you can test whether or not this turns on or off the LED. Once you have that debugged, you don't have to change anything else in the program. Once you have that one, you know that you can turn the LED on and off at will. Then you can go and work on delay N. My recommendation for delay N is that you try a very small inner loop value, like 2-3 iterations, and that you test that you can run that for a certain number of this small internal cycle. So for example, if your cycle is if you pass 2 into N, you can run the internal cycle twice. If you put 1, it's going to be just 1 time. If you put 3, it's going to be 3 times. And once you have that working, then you can ramp up how much you want for the inner loop and tune it for the actual value that you want. Something important here is that value will probably change quite a bit. For example, if you use just the signal analyzer, you can have a very large delay in the inner loop, because it won't be able to fit in the frame, in the buffer that the logic analyzer has to store samples. So it has to be pretty quick when you use the logic analyzer. But if you want to show this to a human, then you are going to have a longer delay internal loop, like hundreds of milliseconds, so a human being can see the pattern coming out of the LED. Then I would recommend that you work on chart to Morse. This subroutine is the one that will take in that character that you read from the input LUT, and you're going to convert that into its Morse equivalent. So in this subroutine is where you have to handle the other array we're giving you, and in that case you're going to have to use base address, base plus offset, to compute the target address you want to read for the Morse code. And then finally, this is the most challenging one, is to process the Morse code that you read from the Morse LUT and convert that into the sequence of dots and spaces that make this Morse code. So that is everything I wanted to say for Lab 2. Remember, you have the manual, you have the reference, you have the comments in the source code, so you should be able to read all of that, follow the hints, be careful with the warnings. There are things that if you do wrong, your program can fail. If that happens, the warnings may guide you towards the right possible solution, because if you do something that we say don't do this, and you did, is the way you can fix it. So this lab is quite complete in terms of documentation. I see no big problems ahead of you, but remember, if you need help, you need any assistance, just go and learn, post your questions on the forums. If you need even more assistance, just send me an email and we'll try to figure out a solution for your case. That's all for today. Thank you very much, and hope to see very great submissions. Bye bye.